All right, let's get right into it. We are about to break down one of the most important concepts in the world of big data, a software framework that literally changed the game for how we handle absolutely massive data sets. We're talking about MapReduce. Hey everyone, and a special welcome to all you computer science students joining us. We're going to unpack Chapter 8 and really get to the heart of how MapReduce works, why it was invented, and why it's so powerful. So here's our game plan. First, we'll look at the problem that started this whole thing. Then we'll break down the two key functions, map and reduce. After that, we'll see how they work together, check out the framework that makes it all possible, and then tee up what's coming next. So, first things first, you gotta ask, why did we even need something like MapReduce? Well, it all started with a problem that our old ways of computing just couldn't handle anymore. This right here, this was the question that companies like Google were wrestling with back in the day. I mean, think about it. You've got the entire internet's worth of data. Petabytes of messy, totally unstructured stuff like web pages and log files. How in the world do you run a single calculation across all of that at the same time without waiting for months? That's the challenge MapReduce was born to solve. The solution starts with the first of our two heroes, the map function. You can think of map as the first wave of the attack. It's all about applying one single simple operation to every single item in a gigantic list. So the textbook definition says the map function takes a list, applies some function to every key value pair in it, and then spits out a brand new transformed list. Now what's really crucial here is that the original list is never touched. It's a non-destructive process, which is awesome because it means you can run all sorts of different maps on the same data without ever messing up your source. Okay, let's make this more concrete. Picture this. Our input is a huge list of every single county in the US, and we want to find all the ones with more than 50,000 people. Our map function is that really simple question, is the population greater than 50,000? That's it. The function just runs on county 1, then county 2, county 3, on and on, creating a new list as it goes. And this new list is just a bunch of key value pairs, answering our question, no for county 1, yes for county 2, and so on for thousands of counties. All right, so map did its job. It transformed our data, but we still just have another giant list. We don't really have an answer yet. And that's where our second hero, the reduce function, steps in. Its whole job is to take all that processed info and boil it down into a final, useful result. So the key thing to get here is that reduce works on the output from the map stage. While map is all about transforming each individual item, reduce is all about summarizing. It takes that intermediate list and just collapses it, combines the elements, and gives you a single clear answer. Let's jump back to our example. Our input now is that list of counties, and each one is tagged as either populous or not, thanks to our map function. Now the reduce function comes in to pull it all together. Let's say we want to count how many of those populous counties also had a Democratic majority. The reducer just iterates through that yes list from the map stage, chucks the party, and if it's a match, it adds one to a counter. The final output, just a single number, the total count. See? We went from a massive raw data set to a very specific, insightful answer. Okay, so now that we've met the two main players, let's see how they work as a team. This is where the real magic of parallel processing comes to life. The entire philosophy behind MapReduce can be boiled down to these two words. You don't try to solve one massive problem on one giant supercomputer. No way. Instead, you divide the problem into thousands of tiny, manageable pieces, and you conquer each of them separately, all at the same time. And this divide and conquer idea follows a really clear sequence. First, as you can see, the initial data gets split up into chunks. Then you've got maybe thousands of parallel map tasks, all getting to work, each on its own little piece. The results from all those mappers are then shuffled and sorted, which is a super important middle step. And then they're fed to the reduce tasks, which put it all together for the final answer. It's like a perfectly coordinated assembly line for data. Okay, for all UCS students, this concept is probably very familiar, and it is the absolute secret sauce that makes MapReduce possible. The map function is commutative. Just like 5 plus 7 is the exact same as 7 plus 5, the order that you run the map tasks in just doesn't matter. And that property is what lets the whole framework distribute these tasks across a giant cluster of computers. It doesn't care which one finishes first because the math works out to be the same in the end. It's brilliant. So, MapReduce is a fantastic programming model, but it's not just a theory, right? It needs an actual engine to make it go, a framework that handles all the messy, complicated logistics of distributed computing. And this is all the stuff that Framework is doing behind the scenes. It's basically the master coordinator. It figures out which tasks should run on which computers. It's smart, so it tries to move the small bit of code to where the massive data already lives to avoid clogging up the network. It manages that critical shuffle and sort phase. And maybe most importantly, it handles failure. If one machine just dies mid-job, the Framework doesn't panic. It just reassigns that work to another machine. It's built for survival at a massive scale. Of course, the Framework itself needs a solid foundation. It has to rely on a distributed file system to store and get to all that data scattered across the cluster. It also needs to be aware of the network and the hardware, knowing which computers are physically right next to each other in a server rack, so it can make data transfers as fast as possible. So, we've covered the problem, the elegant two-part solution, and the behind-the-scenes framework that orchestrates everything. And that brings us to our final, and maybe most important point. I love this analogy because it just gets the idea across perfectly. MapReduce is the programming model. It's the algorithm, it's the recipe. It tells you how to process the data. But a recipe is just words on paper. You can't actually cook anything without a kitchen. You need the ovens, the mixers, the whole setup. And that leaves us with this one big question. If MapReduce is the model, what's the machine? What is the real-world open-source kitchen that was built to actually use this recipe at a massive scale? Well, that's a topic for our next chapter, where we're going to dive deep into the world of Hadoop. Thanks for tuning in.